All right. So right now we're going to look at the fourth and final IB proof, and this is for optics, option G, looking at various situations. We looked at magnifying glasses focused at infinity and at the near point, and then we looked at telescopes focused at infinity. And now we're going to look at microscope focused at the near point. Okay, and so you'll notice that we are again going to have two lenses. We're going to have an objective lens. This time our objective lens has a very short focal length, and then we have an eyepiece lens that has a longer focal length. We're going to again do angular magnification here. So let me remind us that angular magnification is defined as the angle that we actually get for our image as compared to our object reference angle. And our object reference angle, if we recall, is simply if we were looking at an object with no assistance, just with our eye, we were using our near point distance, which is to say as close as we could focus this object, we would have this angle theta, theta 0, which is our reference angle for resolving this image, this object I should say, so HO. We notice that if this angle is small, which it will be, we can approximate the arctangent of HO over D as simply HO over D if we're in radians. And that's what we'll go ahead and do again this time. So if you haven't seen the other proofs, you might want to do that. It'll help as this is the last and hardest of these proofs. So we'll notice what happens here. This first lens does create a real image. This real image right here is labeled I1. This is the initial image. And the thing is that that real image inside the microscope is actually too close to the eyepiece lens. And so since the focal length is out here, we'll notice that we're going to get a virtual image in the second lens, which is to say way back here with our reverse ray tracing. Okay, so what we'll actually see is this inverted but much larger virtual image due to the action of the two lenses, where the first lens creates a real image and the second lens thus creates a virtual image, because the image of the first lens, which becomes the object of our second lens, is inside the focal length of our second lens. Okay, let's look at how the math works out. What we do is we simply say that the magnification is theta I over theta O, and we've looked at theta O already being HO over D, where D is the near point. For theta I, we say, okay, this is pretty easy. We know that we're looking here at the focusing of our eye at the near point. And so we go from the eyepiece lens, where our eye is, all the way over to where this image, the second image, is going to be, which is labeled H2 here. Again, we had our object, there was a real image after the first lens, and then a virtual image on the second lens. So this distance D that we have here is going to be the same as the distance D that we had in our reference back here. So that's going to help us out a lot, because we can see that the D's are actually going to cancel. So let's take a look at how that happens. So our H2 over D and then HO over D, we see our D's cancel. The HO that's in the denominator ends up on top, and we get H2 over H0, which is our initial height of our object back here. Okay, now this isn't useful to us, so we're going to just do a little algebra trick here. And we're going to go ahead and separate the H2, which is on top, with the H0 that's on bottom, and multiply both the top and the bottom by H1, which is to say we're multiplying by 1, and we're not really changing the value of H2 over H0. But now that I have an H1 in the bottom and an H1 on top, I can separate them and think of the H1 over H0, which is simply the linear magnification, right, of the first lens, M1, and H2 over H1, which is simply the linear magnification of the second lens. And so that's very powerful. We can just look at the product of the two linear magnifications if we're after the angular magnification of the microscope. And that's our IB derivation for a microscope. Hope that helps. Please see me about questions with this, and you should be able to do the derivation all on your own, including drawing the ray diagrams, coming up with the original assumptions, remembering to reference to this original angle, and ultimately having our angular magnification being the product of these two linear magnification. This is definitely the hardest proof. You're going to want to practice a couple times. I will say it is rare that IB actually asks for the full derivation from scratch, but the questions that they ask, you can do much better on them if you understand the idea and the functionality here of this microscope. So in any case, good luck, and I hope that helped a little bit.